In this video, we are going to take a look at our first derivative test, which helps us to identify, helps us to classify whether or not a critical value is going to be a relative maximum or minimum by looking at whether it changes from increasing to decreasing or from decreasing to increasing. So if our derivative, so let C be a critical number of a function f that's continuous on an open interval I containing C. If it's differentiable on the interval, except possibly at C, then f of C can be classified as follows. So if the derivative changes from negative to positive, then what does that tell us about the function? Well, it tells us it's moving from decreasing to increasing. Oh, if that happens, if it changes from decreasing to increasing, we must be at the bottom of that valley. We must be at a minimum. And there's a relative minimum at this point. If, on the other hand, it changes from a positive to a negative, right, that tells us it's moving from increasing, and then right at C, immediately after it, it's going to be decreasing. Oh, that tells us we must be at the top of a valley, top of a mountain, right? And we have a maximum. And if it's either positive on both sides or negative on both sides, then it is neither a maximum nor a minimum. So let's go back through to the examples that we've done in our previous couple of videos and see if we can identify places as maximums, minimums, or neither. All right, so let's go back all the way here to this example. Here we have k of x is shown here. We previously found the critical numbers are negative 5/3 and 1. So let's first look at negative 5/3. At negative 5/3, are we going to have a maximum or a minimum? Well, our derivative changes from positive to negative, so it's increasing and then decreasing. So negative 5/3, we must have a maximum. Right, so k has a maximum at negative 5/3, and the y value there is 256 over 27. So that's our maximum. What about at 1? So at 1, our derivative goes from negative to positive. So that tells us our function is going from decreasing to increasing. So 1 must be a minimum. And if we plug 1 into our original function here, we are going to get an output of 0. So we have a minimum at 1, 0. Great. Here, for our second problem, second example, our derivative, our critical point was 0. At 0, our function derivative changed from positive to positive, so it made no change. So if we were to classify that point, we would say 0 is not a max or a min, and in fact, f has no max or min. Right? 0 was our critical point, and it is neither a maximum nor a minimum. All right, let's look at number 3. For number 3, we have 0 is a critical point for number 3. 3 and negative 3, we found those were places where the function did not exist, the derivative did not exist. However, they were also places where our original function did not exist. And so those were both vertical asymptotes. And because they're vertical asymptotes, they're not going to be places of maximums or minimums. Right? So on either side of that asymptote, because it's not actually defined at that point, it can't be a maximum. But 0, we could have something happening. So what's happening at 0, when x is 0? Well, when x is 0, our derivative changes from positive to negative, and so we have our function is going from going up to going down, so we have a maximum at 0, comma, and if we plug 0 into our function right here, plug in 0, we will get 0 as an output. Right? So we have a maximum at 0, 0. We have vertical asymptotes at x equals 3 and x equals negative 3. And let's look at our final example, that example 4. Before we get too far in, notice that 0 is going to be a vertical asymptote. So that's a vertical asymptote. But at negative 1/2 and positive 1/2, we can have interesting things happening. At negative 1/2, our derivative changes from positive to negative. So it's going from increasing to decreasing. So we must be at a maximum at negative 1/2. And the output when you plug in that negative 1/2 is negative 4. And what about positive 1/2? Well, at positive 1/2, our derivative changes from negative to positive. So it's going down and then it's going up. So we must be at a minimum there. And when we plug in 1/2 into our function, we will get an output of, when we plug that in, we get an output of positive 4. So there's a minimum of 1/2 comma 4. Now that might seem strange because we said the maximum is at negative 1/2 negative 4, but the minimum's at 1/2 4. That feels backwards. These are local maximums and local minimums, right? So not global, just locally. So this, relative to everything around it, it's smaller than the values around it. Relative to the neighborhood around this, this is the largest value. All right, come back next time and we will talk about what the second derivative tells us about graphs of functions. We will see you there.